Okay, let's finish this slide, and we say that uh, an equivalent RC circuit, okay, is formed, okay, at the input when your frequency of operation is low. The frequency of the signal is low, and this is the corresponding RC circuit. So this is equivalent R, and this is the C1. Now let's talk about the circuit and the values of R and C. Now over here we say that okay, is let's talk about its critical point or critical frequency, which is FC. How we can what would happen at FC? So over here it says that previously mentioned a critical point in the amplifier response occurs when output voltage is 70% of its mid-range value. So this is by definition the value of the definition of the critical frequency. Okay, now this condition occurs in the input RC circuit when XC1 is equal to Rn. So let's talk about this part. So we can clarify this by saying that what would happen that if this this XC, the value of reactance of this C1, okay, this XC1 becomes equal to Rn. Okay, so this is a case we discuss. Okay, so this formula, we can see this is a voltage divided formula. Okay, and V base, basically we can say this is V base, okay, the voltage over here, and this is the voltage which is V in. So both are related by this formula. Okay, and remember this is any voltage ratio. Remember last time we said V out was equal to for a voltage divided rule at the base, it was, I think, R1 divided by R1 plus R2. Okay, remember this thing. Okay, R2 into V in. So this was basically we studied last time. Okay, R1. Now so V base is across R in, so that is fine over here, and the denominator over here, basically it is the summation of the square of this reactance and this. So basically it is equal to R in square, okay, I can say this is R in square plus XC square, okay, XC square, R in square, this square plus this XC square. It will be the total resistance, okay, in the circuit, okay, XC square, right? And if I so sorry, I can go there. Where is the undo thing or is over here? Okay, so this would be in the denominator, it looks like this, and in the numerator I have R in. Okay, this is R in, which is now equal to, okay, I can say this is V out. You can say V out to make it very similarly to the formula we studied earlier in the previous chapters, V in. Okay, so so definitely if you see V out over here is V base, okay, V in over here is V in, V is input voltage, right? Now what would happen that we discussed that if its XC is becomes equal to R in, so I can put the value of this XC, okay, which is equal to R in. So if I put it over here, so it becomes 2R in square, and this is will be under root 2, and this is R in. So if I take this 1 by under root 2 is 0.707. Okay, now I take V into the other side of the equation. Okay, so the other side of equation, if I take the V in, so basically I would have VB divided by V in, okay, and then equals to 0.707, right? Okay, which is given by this part. If I take the log and multiply by 20 because it's a voltage, so I can get what? Minus 3 dB. So interestingly, we say that if xc1 is equal to Rin, okay, so the gain reduction is equal to minus 3 dB. So if this is the case, it means that critical, this represent what? Critical frequency condition. So the conclusion is that if this Rin becomes equal to the Xc of the reactance, we would have a voltage drop, okay, a reduction in the voltage in this circuit at the input equal to minus 3 dB, and it corresponds to your critical frequency. Okay, so it means critical frequency, okay, for this case, okay, it occurs when Rin is equal to Xc1. Okay, so this is the conclusion. So now if I take this equation, okay, or maybe this equation xc1 over here, okay, and I put the value of xc1, which is 1 by 2 pi fc, and equal to Rin, so I can instantly take out the value of this critical frequency fc. Okay, so this is my relation for, okay, for critical frequency. So it means that if I know Rin, if I know C1, so I can calculate the critical frequency. Okay, and if I calculate the critical frequency, so I would know that at this frequency actually there is a reduction in minus 3 dB voltage gain, right? So next slide, let's do an example. The example says 10.3, again from Flight's book. It says for the circuit in the figure 10.11, calculate the critical frequency due to the input RC circuit. Assume Re this, beta this, and notice the swamping resistor is used. So very simple, it means that this is the circuit given. Calculate the lower critical frequency. So the formula is, lower frequency formula is given by this relation. Okay, due to the input RC circuit. So due to the input RC circuit, so it means that we assume only this part. Okay, so RC circuit formation over here at the base. Okay, and okay, and the other values given are Re prime and beta, and swamping resistor which is used as the 33 ohms over here. So if I remove this, so I can show you over here, this is the swamping resistor over here. Now it's what is the lower critical frequency? So you write the relation over here. Okay, C1, where is C1? C1 is given, so you put right C1. 2 pi is constant. What is Rin? Remember, Rin would be the binary combination of R1, R2 and Rin base. And what is Rin base of this transistor? Rin base of this transistor is what is basically Rin base of this transistor is beta R, beta RC Re prime. But if a swamping resistor is used, so basically it is equal to beta and Re prime plus, okay, Re1, sorry, Re1. This will be your input resistance at the base. So you put the value of R1 is 68, R2 is 22, beta AC is 200, Re prime is 9.6, okay, and Re1, okay, this comes out to be 5.63. So if I put the values, the equation, the critical frequency comes out to be 282. So it means that this is the value where if anything, if a frequency is further reduced from this value, so there will be a further reduction in the voltage gain. But at this frequency there is only a relative reduction of minus 3 dB. Thank you.